Okay, so welcome everybody again for the third day of the CIS Summer School. So today we have again two outstanding speakers that are going to talk about different parts related to applications, and actually the use of memory for 104 different types of uses and what kind of memory you should use. The second one I will now to know is how they can help to do the CIS system. So let's start with the first one. So our first speaker is Professor Mutlu from ETH, and also he is actually a young professor in CNU. ETH, he is the head of the Safe and Fair and Robust and Intelligent lab, which is called Safari, so you have to make it easier. So he's always at the hand of ideas of memory computing and how it can be used. He had a lot of prizes and awards, so I'm not going to go through all of them, otherwise we will not be finishing in the whole morning. I think we'll just say that he's an electrical fellow, an ACM fellow. He has published more than 400 papers. And I think his talk, as usual, will be extremely interesting. We're going to give two parts. So the first part is around 9:15 to 10, and then you will have a little break, and then the second part about resilient memory design. Okay, so with that, I let Onur. It's a pleasure to have you here. Thank you very much for coming, and the floor is yours.
Yeah, thank you very much, David. I think David was perhaps the only person who tried to expand that acronym that I know of, really, publicly at least.
I also know the name, so
yeah. We just go by Safari. Thank you for inviting me, and thanks for coming. We have some time. We have too much material for the time, so our progress will be determined based on the questions you ask. Let me put it that way. Since it's a summer school, I think you have the opportunity to ask questions and determine the speed at which we progress. Normally, I can talk about this for days. It's a topic that I think can cover days. Okay, let me hide this one. Okay, I'm going to give an overview of memory-centric computing. And I think in general, the problem we're having with memory systems and data storage in our computing systems, I think this is really the major bottleneck. And hopefully I'll show you with some evidence from the field. And we have a lot of evidence from the field that this is the major bottleneck in computing systems. And the summer school is especially on machine learning and edge devices, and it's even more of a bottleneck in those applications and the devices. But it's a more general bottleneck also. If you look at computing today, all aspects of computing systems are bottlenecked by data. And important workloads that you look at are all data intensive. They require rapid and efficient processing of large amounts of data, and data is increasing. We can generate much more data than we can process today. And this is true in many fields. Machine learning is one example. Genomics is another example. That's why I put them on the title. But any place where you do data analytics, where you have a lot of devices collecting data, and you need to process them for some purpose. The purpose could be good or bad. And we have all kinds of purposes in the world today. You're really bottlenecked by data. And what we're doing on the data is also becoming more sophisticated. It's not just we're generating more data, we're doing more interesting things on the data, more sophisticated things on the data. So we're pushing our systems to the edge, let's say. And these are some example workloads that are bottlenecked by memory. And these are more traditional workloads, let's say, although people keep adding new workloads to data centers, for example. And these are some papers that I reference over here that show that these workloads are heavily bottlenecked by memory in terms of actually many aspects of memory. It could be memory latency, it could be memory bandwidth, it could be memory capacity. At different times, these workloads are bottlenecked by each of those. Sometimes they're bottlenecked by all of those at the same time. So it's actually very interesting. And when I say memory, it's more general than just main memory. I also include storage there, but we will talk about that distinction a little bit, maybe. I think of memory and storage system as part of a bigger memory system. Of course, there's a huge disparity between memory and storage today that people try to do, try to fit everything as much as possible inside the memory. They're in-memory databases, for example, today, so that they don't go into the storage devices. Keep that in mind. Okay, but basically, it's clear that data is a huge performance energy bottleneck in these workloads. If you look at the more mobile end, that's also true. These are some workloads that we're quite familiar with. We've analyzed them. I'm going to give you some results related to them also. These workloads are also bottlenecked by data, and data actually constrains the performance energy of the systems a lot. I will briefly talk about some more emerging workloads like genomics, which we've been working on for some time. And I think it's quite exciting, especially today with COVID-19, but it was always exciting for me. This is an area where we can produce much more data than we can process. And you can see that there's actually a huge growth in the amount of genomes we can sequence. I don't trust these numbers. It just looks nice, right? It's taken from economists. It's not clear if they got their data fully correct, but this is actually real. This data over here is real, which basically shows that the cost of genome sequencing is reducing greatly, exponentially, where the exponent is much larger than the exponent that we have in Moore's law, where the cost of a transistor is reduced. So the reason is we have technologies that are actually extremely good at sequencing genomes. So this was the introduction of high throughput sequencing technologies where the cost dropped greatly. And this inflection point is the introduction of more nanopore sequencing technologies where the cost dropped greatly again. So you can see that we're dropping the cost of sequencing any kind of genome. As a result, we're able to generate a lot of genomic data. But unfortunately, processing capability is constrained. So basically, if you look at the pipeline of genome sequencing, you need to sequence genomes, and then you need to do some analyses on it. And all of those analyses are computational analyses. It depends on what analyses you do. You give this to a doctor, and the doctor tries to figure out whether a particular drug would be beneficial to this person based on their genomic sequence, right? And they may have to do this very quickly, right? Especially, there are a lot of studies that show, for example, in infants, you need to do this very quickly so that you can basically administer the right treatment so that they can survive. I mean, it could be very life critical, basically. And if this takes a too long time, then that medical treatment can be delayed. Scientific discoveries can be delayed also. So there are two different aspects to genomic sequencing. We can do scientific discoveries, like understand the COVID-19 genome and develop new drugs for it, or develop new vaccines for it. That's one example. But also there are medical examples also. The problem is this machine is extremely good, whereas our computational capability is not very good, mainly because we're bottlenecked by data. And I'm going to give you some numbers also. So we've been working on these devices for some time. This is actually an earlier version of the Oxford nanopore device. You can see that it's very simple. It's also very cheap. The problem is it's a great data generator. It can generate data very well, but it cannot do anything to the data. It cannot process the data. You have to transfer it at least to your laptop, but your laptop is also not good at processing the data if your analysis is actually complicated. And usually your analysis needs to be complicated if you want to do something serious with the genomic data. And our goal has been, when we started this research in around 2007 or so, has been to take this sort of devices, give it to a private person or a doctor, so that they can basically do analyses on their own as much as possible without exposing their private data to the world, so that they can basically do personalized medicine on their own, let's say. But unfortunately, we're not there yet, basically. At the time we started this research, these devices didn't exist. The devices were actually huge genomic sequencers, which already exist, and they're actually extremely good today also, but they're very expensive. But now we're moving genomics to the edge as well, as you can see with these devices. And I think going forward, it's going to be even more at the edge. Of course, there will be a need for the huge devices always, because they have different characteristics. I can talk about genomics also a lot, but we don't have time for this. My point is, these are real devices that exist, and there are real applications for it. Again, if this were a talk on genomics acceleration, I'd talk about those more. And you can find some of those applications and analyses in this paper, for example. That's relatively dated right now. It's a few years old, but the fundamentals still remain. So the takeaway is you have this special purpose machine for sequencing, and this is the big device, as you can see. It's very specialized, and you have a general purpose machine for analysis, and that doesn't match up, basically. It's not just because it's, so there are two reasons why it doesn't match up. Because one is this is general purpose. We send it to data centers, for example. It becomes extremely inefficient. You get your analysis after 2 weeks, which may not be good in many cases. So we need specialized machines, and we also need to treat data in a better way. So if this machine could do the analysis in itself, the data movement would not become a huge bottleneck, basically. And this talk is really about not moving data, let's say. I could have easily retitled this talk as data minimizing computing, or data movement minimizing computing. Okay, so if you're interested in this area, there's a lot of work. This is a summary paper that we wrote again 1.5 years ago that talks about the efforts that are going on in the field. You can take a look at it. And we've been looking at FPGA-based acceleration of this sort of applications, as well as other applications like climate modeling, weather modeling. That's also very interesting. Another application where we have a lot of data and we have to sort through it. And you can take a look at that in this paper. I will give you just to motivate what's coming next. We actually did this, this paper summarized some of the work that we have done. We actually did this together with IBM, and we had access, and this is data based on real machines. So we have the CPU, a very powerful CPU, and then FPGA board that has access to very high bandwidth memory. It's called HBM. So this FPGA, if you can think of computation that you can do in this FPGA board as near memory computing, right? Instead of doing it over here, you offload the computation over here, and you configure your circuit such that it matches you, they match your application's core kernels. And we did that for weather modeling and genome analysis. Just to give you an idea of what kind of results you get, even in existing systems today, which is this one, it's actually quite significant. By offloading computation carefully and specializing the computation near data so that you minimize the data moment as well as accelerate the computation, you get significant performance improvements and energy efficiency improvements. So these are examples, real examples from real systems on two workloads, weather modeling and genome analysis. And more details are in the paper, of course. So I can give you some more examples, but we don't really have time for at least the genomics part of this talk. But there are a lot of interesting things that you can do. And these are all, again, data bottleneck. So approximate string matching is really at the core of comparison of multiple genomes. And you can accelerate it near data as well. More recently, we had this work on in-store genome filtering because while you're doing building these accelerators, data movement from storage to memory also becomes a bottleneck. So if you can actually cut the data movement, whenever it's happening, you get a lot of efficiency. So storage is one place. In fact, sensors, that's what we're pushing forward with. If you can do the data movement, if you can minimize the data movement at the sensing point, which is in the device itself, either in the large devices or the small devices, you can actually gain a lot more efficiency. So the closer you get to the data source and data storage, and the closer you can do filtering or computation over there such that the data doesn't move to the other parts of the system, you get a lot more benefit that way. And to put this in perspective, it's not just that a single system, right? You may think, okay, you have this genome sequencer sitting here and you're communicating here, but this is the micro scale. There's a macro scale also, which is you have these genome sequencers all over the world, and they're sending their data to the data centers, and that data, the analysis gets communicated back to, again, edge devices, let's say, these computers. So we're basically wasting a lot of energy and performance potential at the micro scale as well as the macro scale, because we really don't have the right computation capability placed next to the data where it's generated or where it's stored. Okay, this is one example. And this is coming up at ISCA next week. It's going to be presented. And there are a lot of interesting issues that I'm not going to talk about. And these are some more recent nanopore devices. There are more coming up, so you can actually put them on your phone. And these are great data generators, as I mentioned. So I can talk more about this, but we have talks and classes on this. If you're interested, you can take a look at them. And some more recent ones are not included over here. You can find them online. But this was just an example application that I believe is going to be increasingly important going into the future. That shows that data today overwhelms modern machines. It overwhelms the storage and memory capability because we actually need even more storage, bigger storage to store the data. And there's no end to this, it seems. And it overwhelms the communication capability. As I said, we're moving data all around at the micro scale and the macro scale. And in the end, it overwhelms the computation capability. You may have a perfectly capable, very, very strong computation engine that's specialized. And we have these devices, or general purpose. We have these extremely good devices today that are actually like we never had before, right, in the history of human beings. But these machines are waiting for data. I'll show you a lot of data on this also. You may have this computation capability that's essentially not used. And also data greatly impacts robustness, energy, performance, and cost. And we will talk about that a little bit. Okay, so let's go back to the fundamentals of it. There are three key components to a computing system. You need computation, communication, and memory and storage. And if you look at the history of computing, over decades, we've heavily optimized this computing unit. This computing unit today is actually very sophisticated. It's not just a general purpose CPU. It could be FPGA, GPUs. It could be many, many different accelerators, machine learning accelerators, but vision accelerators, audio, video accelerators, etc. And today we have heterogeneous system on chips that integrate essentially all of them together, right? So this computing unit is very sophisticated. We've focused a lot on it. Comparatively, we haven't focused on the rest of the system. And that's why we're having a problem today. And this is my cartoonish picture of it. This picture I can still use. It's actually 15 years old or so. This was from one of my first NSF proposals in the US. Basically, this shows that you have a node, single node, looks general purpose, but it could be specialized. These cores can be specialized also. Computation is done only in the cores. Everything else, the caches, interconnects, caches, scratch pads, interconnects, shared memory, memory controllers, interconnects, main memory, interconnects, storage, everything else is there to store and move data. They're not capable of doing computation. So if you do the calculation, actually, even less than 5% of an entire single node is dedicated to these computing units, even though we call these computing systems, right? Most of what they do is storing and moving data. And even, I didn't even talk about what's inside the cores. What's hidden over there is a lot of memory. L1 caches, registers, and GPUs register files are huge, for example. In machine learning accelerators, the scratchpad memories are huge. We will talk about that hopefully when we get to it. So essentially, in all of the systems that we're building today, most of the system, the real estate, the hardware real estate, is dedicated to storing and moving data. Yet the system is still bottlenecked by memory. So there seems to be some imbalance here, right? We're putting so much effort on storing and moving data, yet we're still bottlenecked by data movement. And this talk is about basically how do we fix that? And if you don't believe my picture, I like using some real examples. This is AMD's more recent, one of the recent chips. You can see that this is all, even the processor chip is all about caches. And if you don't like that, there's even more. 3D stacking, more caches. Right? So I think this is a bit sobering to me, at least, to look at these pictures and say, okay, are we doing the right thing by building these systems? And they're actually, I mean, it's great actually. I like this a lot because people are pushing the boundaries of what you can do with 3D stacking and putting more caches. And these caches, when they're useful, that's good. Like on some of the gaming workloads, they provide 15% performance with a 64 megabyte cache. But maybe we shouldn't be satisfied with that, right? That's interesting. Anyway, okay, so you can take pictures from other companies also, and it's all the same basically. And we're not looking at all the memories. I circle over here just the L3 caches and part of the L2 caches. Okay, so data essentially, basically we're building these machines that are computing systems, but they're really data storage and movements, data storage and movement systems. And as a result, data moves a lot. On these workloads, we did some studies on real systems, and we found out that more than 60% of the entire system energy is spent on data movement. And these workloads clearly, I believe everyone here would be using versions of these workloads, right? Maybe not the Google version, but some version of these workloads. And even if you don't like it, your phone is using some inference engines and maybe monitoring your actions. Okay, so my axiom and the rest of this talk is that an intelligent architecture has to handle data well. Then the question becomes, and we want to build intelligent architectures because these systems are going to make decisions for us. Right? They may make health decisions like we have discussed. They may make like even bolder decisions like self-driving cars, right? It's not clear if we can trust these systems very well. The question is, how do we handle data well? Right? There are three directions to it. I'm going to mainly focus on the first direction, which is ensuring that the data doesn't overwhelm the components. But the other directions are also very important, in my opinion. If we have time, we can talk about it, but probably we're not going to have time because the first one has a lot of interesting things in it. So we should ensure that data doesn't overwhelm the components. But what does this mean? We need to design intelligent algorithms. We need to really think across the stack for this. Intelligent architectures, not what we have seen, I believe. And more importantly, whole system designs that match the algorithm architecture and the devices so that you can really specialize things. Because as I showed you the earlier picture, if you have a special purpose technology that generates data, you cannot keep up with it with the general purpose technology. That's what we've been uncovering, at least in our research in genome analysis, for example. The second direction is we should really take advantage of vast amounts of data and metadata. And today we're not doing a good job because the systems that we build are very much human driven, meaning a human sits and designs the controllers in it, right? My favorite example is a memory controller, since we have done a lot of research on memory controllers. There's a memory controller in this machine. It's not that old, but I have a cell phone that's 6 years, 7 years old now. There's a memory controller. Memory controller has seen a lot of applications, has observed, well, not consciously, but could have observed my behavior over the course of 6 years, 7 years, or even microseconds, milliseconds, etc., and could have changed its policy so that it could have a better policy over time, like humans do, right? Humans are agents of reinforcement learning, machine learning. We interact with the environment, everything we see, and we learn. We change our actions based on feedback from the environment. But the controllers that we have in our system don't do that. They're basically designed by a human who has dictated some actions based on some very limited information about the system, usually about the component that they're dealing with. So for the memory controller designer knows very well about the memory banks, robuffers, channels. So they basically hard code very simple policies that say, if the robuffer is open, schedule this request that goes to that robuffer. If the robuffer is closed, pick the oldest request, for example. So these are very hard code action policies that cannot adapt to the data that's flowing through the system. And maybe we need to change that. If the data is what's important, we really need to learn from the data and adapt these controllers to become much more intelligent, let's say. And I think this is actually a fascinating area where we rethink how to design the system such that the system evolves over time and learns a much more intelligent agent, basically. Today, we don't have that. The memory controller is doing exactly the same thing it was doing 6 years ago, even though it had so much experience. If you think about, if you apply that for humans, that would be completely unacceptable. You probably don't want to be doing what you were doing when you were born. Okay. And the third direction, which is also important, is we should really understand, exploit properties of different data. Basically, data has lots of semantic and performance and reliability properties. Today, those properties either don't get discovered or don't get communicated to the underlying levels. For example, different data has different security properties, privacy properties, approximability properties, error tolerance properties, performance properties, even locality properties, right? So that information doesn't get communicated in the underlying architecture. So again, my favorite example, so the memory controller doesn't know this information. So when it makes a scheduling decision, what it does is it says, oh, is the bank busy or not? Is the robuffer open or not? It doesn't say, is this data the more important thing to service or not? Because it doesn't know. So that information doesn't get communicated to underlying components. As a result, we make decisions that are not, I would call not intelligent, basically. Okay, so basically, I think I've already talked about this. Today, we're not good at dealing with data. We're very processor-centric as opposed to data-centric, so data moves a lot. We're going to focus on this one. But these two other directions are very synergistic. Today, we're not good at learning from the data in the design of our systems. Systems are designed to make human-driven decisions as opposed to data-driven decisions that evolve and become better over time. And again, today, we do not know enough about the data in the underlying architecture. And when I say architecture, it actually encompasses not just the hardware. In the hardware, these issues become extreme, but also a lot of the software stack as well that runs the applications. So as a result, we make component-aware decisions as opposed to data characteristic-aware decisions in our systems. And I think going forward, we really need to essentially do all of these, become more data-centric, data-driven, and data-aware. And as I said, I'm going to talk especially about the first one, but I think of these as all synergistic together. And if you actually can put all of these together, you can do much better. And again, this may sound daunting because you really need to cut across the stack. And I agree that you need to cut across the stack, but I think this is really important to do. Basically, we need to revisit the entire stack. Maybe we can get there step by step. I'll give you some very simple examples that are based on this philosophy that do not require a lot of changes, let's say, but some of the examples will require changes to the entire stack. And we have yet to discover even more examples, in my opinion. So basically, we need to take a much more expanded view. I already mentioned a lot of this, so I'll skip this one, to enable systems like this. And if you're interested in a very short paper that talks about this vision, you can take a look at it. It was an invited paper at DATE last year. Okay, so with that, let's jump into data-centric or memory-centric architectures. Any questions? Okay, no one is at least fully sleeping yet. That's good. That's an issue with morning classes. In general, I don't teach in the morning. So I'm the one who's sleeping. Yeah. Okay, so let's jump into this data-centric architectures. Even if you look at just data-centric, the question is, what does it mean to be data-centric now, right? And these are four major things that I have come up with. There may be other aspects of this, but I think we need to satisfy the first one. We're going to talk a lot about that, processing data where it makes sense, meaning where the data is generated and where data resides. But we also need to design our systems to, let's say, respect the data, meaning if the data access is taking too long, then, and the data is the most important thing, then you're probably not respecting the most important thing in the system, right? So we need low latency and low energy access to the data. And this is correlated with the first one, but independent also, because you don't have to process the data where it makes sense to make the latencies and energies lower to access the data. There are other aspects to it, which we're not going to talk about. I think, again, data, if the data is king, let's say, or queen, it needs to be low cost, right? Somehow you need to not punish the access to data. And there are a lot of ideas over here that we're not going to talk about. I'll mention hybrid memory in a different context. And then we need to intelligently manage that important resource. We need to have intelligent controllers handling robustness, security, cost, and performance. So I'll mention some of these, but we'll mainly focus on the first one over here. And I call it processing data where it makes sense because basically today we have no choice. We have to process in the processor. Processor for me includes all of the accelerators, beautiful accelerators, computing units that we've been building, and no other choice. We cannot even process data inside the cache of an accelerator. We have to move it to the compute unit on chip to be able to do that. But it'd be good to have options basically in the system. And then we need to decide where to process the data if we have options. And this is not a new idea, actually. This is an old idea. You can even go back earlier, but these are some more explicit papers that call it out as logic in memory. And people have envisioned this. This is another paper by Harold Stone in 1970. If you find other papers, please let me know. I like going back to the original sources of things in general. But today we need to revisit it. And I'll motivate it in two directions because so it hasn't panned out for a long time. There are multiple reasons. One of the reasons why we weren't pushed too much by the technology, because technology scaling went very well for us. Today, it's not going very well. Today, we're actually having a lot of difficulties with the technologies, especially memory technologies we're designing, but also compute technologies. And applications have never been as intensive. So basically, we're kind of getting squeezed in the middle. Applications are pulling us, technology is pushing us, and we have to do something different if we want to get rid of the huge energy and performance waste that we've been inflicting upon ourselves in our systems. Let's take a look at the technology aspects. I'll try to cover this relatively quickly. But basically, DRAM is the major memory that's been built to store data in main memory, and it has not been scaling very well. I'll give you some examples of this. As a result, people are, industry especially, is very open to new memory architectures, and academia also on top of this. That's why processing in memory research has exploded in the last 10 years or so, let's say. So let's take a look at this. So people are building 3D stacked architectures. As you can see, I showed you the AMD's last level cache. It's not used in a, let's say, a data-centric way, but you can actually put computation units over here. So these are real examples from industry. Subhashish is doing the 3D, monolithic 3D, which is actually perhaps the longer term way of doing it so that you can actually immerse computing with data. There are other examples from industry, and there are more recent successful examples also, well, successful in the sense that people have put computation units inside the DRAM, which we're going to talk about. And more companies are also introducing accelerators that are more data-centric inside the DRAM. So there was a mindset at even 10 years ago saying that, oh, you cannot put stuff inside DRAM. Now people who are saying, were saying that 10 years ago are putting stuff inside the DRAM. It's prototype, yes. These are Samsung and SK Hynix, two big main memory companies. They're actually changing the DRAM a lot to put accelerators near the memory banks. And there are other examples. Also, you can see Alibaba has an experimental DRAM chip as well. We'll see if it succeeds, but people are trying. And that's basically the technology scaling direction. So there are reasons for it. We've been working on this topic for some time, and this is one paper that we presented some time ago in the International Memory Workshop. At the time we presented this, we didn't have a whole lot of data, let's say, but we collected a lot of data from real systems, and I'm going to show you some of that data that shows that DRAM, especially dynamic random access memory technology scaling, is not going very well. And if you look at the DRAM, How many people are familiar with DRAM here? Dynamic random access memory. How many people are not familiar? Don't be shy. Okay, so DRAM is the technology that you use to build main memory today. All of our main memories are dynamic random access memory. So this has DRAM in it, this has DRAM in it. This, basically, it's huge. It's all over the place. There's no other technology that has replaced it so far. And it all depends on the correct operation or reliable operation of this memory cell. Every memory technology needs to have a storage device. In DRAM, it's the capacitor, and an access device. In DRAM, it's the access transistor and all of the sense amplification circuitry around it. And if you want to make this work, both of these structures need to work reliably. And if you want to make this high capacity, you need to reduce the size of it. If you reduce the size of it, it's reliable to reduce this. Basically, both of those structures start not working very well. So for example, if you reduce the size of the capacitor, you can store less charge. As a result, it becomes much more vulnerable to noise effects, so reliable sensing becomes difficult. If you reduce the size of the access transistor and the sensing circuitry, you have similar issues in terms of retention time and also noise issues. As a result, as you reduce the size of this to very small technology nodes, we're around, let's say 15, 14, 13 nanometers today in the cutting edge, it becomes very difficult to maintain these reliability curves. And this is really the technology scaling problem. I mean, it's similar in many other technologies. DRAM is just one example, but DRAM is a very good example because everybody has DRAM. So we've been doing studies to understand the implications of this. This is a large-scale study that we did with Facebook some number of years ago. We basically analyzed all of the memory areas that they have in their data centers across all over the world. And this is a lot of memory, a lot of data center, a lot of machines. And it's a correlational study because of the nature of it, because data centers are running production workloads. We cannot change things. But the correlation is very strong. Basically, this is the correlation of the chip density, memory chip, DRAM chip density that's employed in the server, and the failure rate that you observe in the server. So you can see that there's a very strong positive correlation. As the chip density increases, meaning cells become smaller as well as closer to each other, you get more server failures because you get more memory errors. And there's a lot of data that we analyze that I'm not going to bore you with. You can read the paper if you're interested. And this is relatively old. And this problem is basically becoming much worse. So the problem is the cells are smaller. As a result, they're much more vulnerable to noise. So there are other issues that I will talk about, but maybe I'll mention one thing briefly, which is another reliability and robustness problem. You can also induce errors in most DRAM memory chips in a predictable manner. And this is the DRAM RowHammer problem. How many people are familiar with RowHammer? Just out of curiosity. Okay. I will not go into detail, unfortunately, we don't have time, but this is a motivator for why we need more intelligent controllers near memory. So RowHammer is the fact that it's a simple hardware failure mechanism. It can create a widespread system-wide vulnerability because you can induce bit flips predictably in these DRAM cells that I showed. And people are writing articles that look like this. So let's take a look at this. So this is a read disturbance phenomenon. And whenever you're reading a DRAM row, you should just be reading that row, right? Reading data out of that row. You should not be changing any data value in memory. But it turns out because the cells are too close to each other, there's coupling between them. As a result, you change data while you're reading somewhere. Yes. This should not happen clearly. This breaks all of the security primitives that we build on top of the memory isolation characteristics that we assume from memory. So in DRAM, this manifests itself as what's known as RowHammer right now, but you could also call it DRAM read disturbance, which we called in our original paper. Basically, you apply high voltage to a row so that you can share the charge of the cells with the sense amplifiers and read the cells. And then if you apply low voltage to this row, you pre-charge the array and you restore the charge. As a result, everything stays nicely, but you can read the row that way. Now, if you keep doing this repeatedly, this is called activate pre-charge in DRAM. High voltage, low voltage, high voltage, low voltage, high voltage, low voltage, high voltage, low voltage. And this could be based on a pattern that you could induce in a real program. I'm not going into the details of it, but real programs can do it because you're reading from memory, right? It turns out some cells in physically adjacent rows become corrupt, meaning the data value becomes, that used to be 1 becomes 0, or 0 becomes 1, depending on the encoding you employ in terms of what you attribute to the charge capacitor or not. So clearly this should not happen because these cells may belong to some other application, the operating system, or some weights in your neural network that you're trying to accelerate, right? Okay. So this is the RowHammer vulnerability at the core of it. And this actually happens in more than 80% of the chips that we tested at the time. It's still happening, but I will not give you the history because that's not the purpose of this talk. So basically, one can take over an otherwise perfectly secure system this way, by manipulating these actually precharges with a malicious application, let's say. And there are many interesting examples of it, which I'm not going to go into. If you're interested, I would recommend this Google blog post. They basically built on our work, and they basically show that you can gain kernel privileges on x86, 64 Linux system just by exploiting RowHammer in an intelligent way. It sounds fascinating, right? Now, more aligned with this summer school, let's say, people have shown a lot of security attacks. Maybe you're not interested in taking over the system. Maybe you cannot fully take over the system, which is a very difficult thing to do, actually. But you can also induce bit flips in machine learning accelerators or a machine learning system. And there are multiple papers on this. These are some example papers. There are more papers. I like this one with a picture that shows that an otherwise perfectly good neural network with a reasonable accuracy may become useless and harmful and a huge safety problem, actually, because your accuracy drops down to, let's say, 10% or some unacceptable level, basically, because somebody is doing this RowHammer attack maliciously on you. And I think this is another aspect of technology scaling that I think we should really consider going into the future, because we're going to rely on our devices that are going to be scaled into these technology nodes. And if you have this sort of vulnerability in your machine learning device in this particular case, that's probably not going to be acceptable. But the reason I'm talking about this is really a scaling problem that motivates us to solve the problem. And I think the solution lies in more intelligent controllers. Of course, there's a huge solution space that we're not going to talk about. If you're interested, we have written papers, and this is a more recent talk. If you want a really summary of RowHammer, this is a 20-minute summary of RowHammer, 10 years of RowHammer research, and it's still going on. So, and these are the papers that you may want to take a look at. This covers actually research across the stack from the security community, from applications community, from architecture and more low-level device and circuits communities as well. Okay, so this is, we need an intelligent control actually to solve this sort of scalability and reliability issues. That's what we've been arguing. And people have been actually designing these controllers right now, either in the memory controller or inside the DRAM chips. Today's DRAM chips actually have RowHammer protection mechanisms. They may not work perfectly well, but they try to protect you against RowHammer internally. And that's an example of an intelligent controller inside the memory chip, trying to do, let's say, the right thing, but they may not be doing the perfectly secure thing because of the design issues, let's say. Okay, another example of scaling, technology scaling problems that I believe requires intelligent controllers is that something that looks like this. Because you don't have a very scalable technology, DRAM is probably not the most scalable technology. Maybe you augment it with some other technologies that seem to be more scalable. Or maybe design DRAM in different ways and put together multiple different types of DRAM in your system. And this is also already happening. If you design a system like this, now you have what's called hybrid memories. And you try to design your hardware and software together so that you exercise the greens of each technology as much as possible while avoiding the reds of each technology as much as possible. And hopefully you have complementary greens and reds in the technologies. And if you think about this, the controller that sits over here that controls these memories potentially together needs to be intelligent. It needs to understand the characteristics of memory technologies. It needs to understand the characteristics of the workloads and the system, maybe the user requirements. So it has to really make decisions based on that information. It cannot be the controller that just says, I'm going to just focus on the timing parameters of DRAM and not bother with anything else. So this is another thing that's driving intelligence in the memory controllers. At least better design of memory controllers, let's say. Intelligence is, of course, a difficult thing to define, right? Okay, there are more examples that I can give you, but let's switch to some other parts. So RowHammer solutions require intelligent controllers. And if you're interested, I will point you to one paper that industry has written on this topic. Industry normally doesn't write papers on this topic as much, let's say, at least at the architectural level. And definitely Samsung and Intel don't get together and write papers on this topic. But they have done it in 2014. And they basically said, we're having a lot of difficulties scaling DRAM technology into the future. And maybe we should really be co-architecting DRAM and controllers together. And that's what we have been also proposing for some time. And we've also been doing a lot of other interesting things. This is one of the recent examples on understanding error correction codes that are employed in existing memory chips. So this paper actually in 2014 proposed error correction codes inside the memory DRAM chips in particular. And people have put error correction codes inside the DRAM chips. That's one very simple example of, I don't want to call it intelligence, but intelligence compared to not having error correction codes, let's say. The question is, can you use these error correction codes so that you can uncover some uncorrectable errors also? And we've tried that, and that requires an intelligent controller also. And we've been building these intelligent controllers for other technologies that have not been scaling as well. NAND flash memory is a memory technology that we all use, right? That actually it's one of the most successful memory technologies. That was an emerging technology for decades, and it became, it really revolutionized our lives by finally emerging. And but this technology doesn't work very well. So you need to build an intelligent controller to make it work. And there's a lot that goes into it. And if you're interested in some of the algorithms that are employed, this is one paper that we wrote. I find it fascinating. And if you think emerging technologies don't have this problem, they all have this problem, basically. You need some intelligent controllers to fix the reliability and scalability issues. Basically, these technologies cannot work alone without the assistance of an intelligent controller that make them work. Okay, so that's, let's say, long introduction was about the technology scaling push. We need intelligent controllers to avoid many failures and enable better scaling into the future. And this was never as huge of a problem before, because DRAM was scaling much better, but 60 years after its introduction, 55, 60 years after its introduction, now it's not scaling as well. So maybe we need to really think about it in a different way. So that's the push from circuits and devices. Now, before we take a break, let's take a look at the, can I take 5 minutes before the break? That would be a nice ending. Let's look at the systems and applications as well, because this is maybe even a bigger pool. Because today's systems are a lot more bottlenecked by data access. I will show you some real numbers. Energy consumption is a huge limiter today. And today, data movement energy dominates compute energy much more than before. I think, like, philosophizing, do we want a world that looks like this or this? I think I'll pick the previous one that looks more like Lausanne. But I should also say that we should have the best of the worlds, let's say, meaning we want energy efficiency and sustainability, no question about that, but we don't want to give up performance. We want all at the same time. We're very greedy. And there is a way we can get all at the same time if we really focus on the fundamental problem. Today, basically, we have data access and we're moving data all around, as I mentioned, and that wastes energy a lot. That wastes performance a lot. We're trying to overcome the performance loss that this data movement brings by adding a lot of complexity to our systems, into the hardware and the software. We're adding, for example, in the hardware, we have heavy out-of-order execution, multi-threading, prefetching, huge hierarchies that I showed you, keep building on caching and caching and caching, and they all add up to the energy waste. So we're in this vicious cycle. We have this energy waste. We're compounding the energy waste by adding more complexity into the system, and it's basically out of control from my perspective. And the fundamental issue is processing of data is performed far away from the data, and we're trying to patch it up in our systems, and we're not doing a good job because all of this complexity that we're adding to the system, sometimes it's benefiting really well. Most of the time, it's not benefiting many of our applications. I gave you the result, an example from this AMD's 64 megabyte 3D stack cache, right? 15% performance on a gaming workload that is designed to include. You're wasting this huge 64 megabyte cache for 15% performance improvement. Doesn't sound like the best thing to do, let's say, especially if sustainability and energy efficiency are our goals. So I showed you this picture before. This is because we're processor-centric. All data has to go to the processor or the accelerator, pick your favorite processor, let's say, at great system cost. And everything else is incapable of processing data. Yet we know that there's a real problem. We just need to somehow change it, right? So this is Dick Seitz, who was the chief architect of alpha processors in the 1990s. His team designed the flagship alpha processor, and he wrote this one-page article in Microprocessor Report, which is titled this way, basically, it's memory stupid. And he basically says, we designed this processor over a decade, and this processor is capable of finishing 4 instructions every clock cycle, but it's finishing 1 instruction every 4.7 clock cycles in this important workload that we wanted it to work well on. It's a database workload. So it's basically operating at 5% of its peak efficiency, peak throughput. And he basically ends the article saying, I expect that over the coming decade, memory subsystem design will be the only important design issue for microprocessors. This is his perspective. Okay, fast forward about 10 years. This is data from my own PhD thesis, my first paper actually. We did the study with Intel. We looked at the workloads that they used to design their processors at the time. And essentially, we found something very similar. Most of the time, the processor is waiting for data. It's doing computation a very small amount of time. And you can read more about both of these papers, and this is our paper. And since everybody believes Google, Google has also published data on this. And basically, they show that the state-of-the-art processor that they have in their data centers running their state-of-the-art data center workloads essentially is doing the same thing, meaning waiting for data. It's finishing instructions, committing instructions only 10 to 20% of its time on all of these data center workloads. And these are actually very, very capable processors. Right? This is the state of the art at the time. Okay. This should probably think us that we're not doing something correctly. Right? These are computing units and they're not computing most of the time. And this Google paper, I would recommend you can take a look at. It's a bit dated right now, but the same thing happens. If you do the same study today, you'll find the same thing today. And we've been doing that with many workloads. So basically, we are processor-centric. As a result, we're grossly imbalanced. So we're violating a very basic principle that we teach in our design classes, right? You talk about balanced design. But all of our computing systems violate that balanced design principle from the get-go. Because you're not balanced. Processing is done in only one place. As a result, data is moving all around at the micro scale as well as the macro scale in the systems. As a result, we're energy inefficient, low performance, and complex. And we make things even more complicated to tolerate this. But as I said, it's not always working. In fact, if you do the thought experiment, if all of your accesses are completely random, none of the mechanisms, well, except for, let's say, multi-threading and maybe out-of-order execution, will make it work. So these huge caching hierarchies are all useless based because they bank on the fact that your accesses are not random. Right? And in many workloads today, we actually have a lot more random accesses compared to the past. Graph processing is one example. And graph processing is at the core of some of the machine learning frameworks that we built. So as a result, we're back to the picture that I showed you earlier. Most of the system real estate is dedicated to storing and moving data, yet the system is still bottlenecked by memory. And we keep basically making this worse and worse. Okay, let me give you the energy perspective quickly. This is data I borrow from Bill Daly. The numbers have changed over time, but the relative the difference did not change. So basically, this is a 64-bit double precision floating point operation, a complicated arithmetic operation, 20 picojoules with some technology assumptions. It's a memory access, DRAM read or write, 16 nanometers. That's 800x difference. So data access consumes 2 to 3 orders of magnitude the energy of a complex addition because you're exercising these huge interconnects. And I think this picture is actually an example of the success of technology scale. This has improved very well because technology scaling enabled us to make the transistor faster and more efficient, but the interconnect did not scale very well. As a result, we're actually having a lot of problems with energy. And if you want to look at even a simple operation, this is a simple add, and this again from another paper on machine learning acceleration actually. A simple add is much less efficient compared to a DRAM access, at 6400x. Okay. As a result of this, most of our systems are spending their time on data movement and energy on data movement. Okay, so I will argue that we do not want to move data. We want to design data movement minimizing machines going into the future. But this requires a paradigm shift in terms of essentially everything, thinking also. Maybe we can get there step by step. We want to enable computation with minimal data movement, compute where it makes sense, enable computation capability all across our different parts of the system. In the sensors also, wherever the data gets generated. But I showed you the example of the genomic machine, for example. Some of those have light sensors. The Illumina machines have light sensors. While you're actually sensing, you can do computation as opposed to moving the data somewhere else and trying to understand what's going on. Nanopore is another example. So we want to make computing architectures more data-centric. So what does this mean? I'm going to talk in the second half about processing inside main memory, because main memory I think is quite interesting, but you can generalize this to everywhere. Main memory is quite interesting because we have huge amounts of memory today in our systems. Even in a like consumer system, you can have a lot of memory. And people design their applications to fit main memory. So wouldn't it be nice if instead of the processor or the accelerator doing everything, it sends a query to the memory saying, memory, can you do this computation for me? And the memory says, yes, here's the data, here's the result. And then they communicate nicely so that data movement is minimized. Of course, there are many questions over here, and it really cuts across the stack. How do you design the system, controllers, memory, processor, communication units, software and hardware interfaces to enable this? system software compilers and languages to take advantage of this in the best way possible. And algorithms and theoretical foundations of computing also, because the algorithms that we use today may not be very good fit for the computation capability that we provide in memory. We're going to talk about that in the second half a little bit more. It depends on what you put onto the memory side. And because you're pushing computation inside the memory, your algorithms need to change as well. I will pick on the theoretical foundations also, because I think this is an example of how the processor-centric paradigm is ingrained in our thinking. How many people have taken a theory of algorithms class here, or theoretical computer science? Okay, that's a good fraction. And when you do, what do you do in that theory of algorithms class? When you actually analyze the complexity of an algorithm, you count operations, right? In general, the big O notation, big theta notation. It's all about counting operations. It's very processor-centric, basically. That's the processor that performs the operations. Basically, we don't have a very good, well, I think we don't have a data-centric theory of computation. Maybe we should not be counting operations. Maybe we should be quantifying the effect of data movement on the algorithm, right? We need to build a theory, algorithmic theory, complexity theory that takes into account data. There are some efforts in this direction, but they're also very processor-centric. That's the interesting part. So basically, all of what we're doing is from the very basics, as I said, from the get-go, processor-centric. Okay, so in the rest of this, let's say the second half, we'll talk about some examples of processing in memory. This is a paper we've written. We're going to update this in a couple of weeks, I think. But we're going to see some examples. And please ask questions, otherwise I'll keep talking. It's a good time to stop.
There is a room for one or two questions now. I suggest that if you have more questions, you can start the next part with the questions of the audience. It's okay. So now I ask a small break and we start at 10:20, let's say. We have 10 minutes of break, and then we are waiting for you for the next part of the lecture.
Okay, thank you. Sure, I'll come.
So now we are here for the second part of the lecture. After that, we are having a small break. So now, if you have any questions for the first part, please welcome.
Okay. Yeah, that's a good question. So people have proposed solutions all across the stack, from the device and technology level to controllers and system software. And there are solutions at the system software that try to detect these patterns using performance counters, for example. The difficulty is it's hard to have these performance counters exposed to the software and react very fast. It depends on your threshold at which you need to react. For example, when we did our earlier studies, the number of activations, row activations to induce a bit flip was around 100,000 or so. But more recently, we repeated some of those studies in recent chips, and some chips get a bit flip after, let's say, around 10,000 hammering. And your software needs to count these accurately, not miss any of them if you don't want any bit flips, and also react quickly so that it can fix the issue. So I think the software response times are not good. And people have shown that these solutions usually have some issues. They're not perfectly protecting against RowHammer. And it's going to be much more difficult in the future as the RowHammer threshold, the number of activations to induce a bit flip keeps reducing because it's a technology scaling problem. So people are looking into some software. So there are another set of solutions that look at isolation, for example. Can you isolate security critical data from non-security critical data by having some isolation rows? Again, technology is not on your side in these solutions. First of all, you're wasting a lot of memory because you're not reusing that memory. that's between security critical and non-security critical data. And how do you distinguish between security critical and non-security critical becomes a problem. And the effect of RowHammer within a subarray increases as technology scales to smaller nodes. So how many rows to protect, how many rows to buffer, isolate from each other becomes a, let's say, I don't want to call it a difficult thing to determine, but it affects your efficiency significantly. So you can imagine other software solutions perhaps, but usually it's harder. If you have hardware, it's going to be a lot easier.
Before you were mentioning possibilities like the smart memory controllers. So is there a problem of dealing with outliers or unforeseen situations in which something which maybe very smart can act in a very strange way?
Yeah, you mean a memory controller that can learn from its actions and adapt over time? Yes. Yeah, certainly that's possible. As long as it's correct and it doesn't affect correctness, it may be okay, right? We're all as humans exploration systems also, and you learn from that action, and you learn not to do that action. Right? As long as the system is the mechanisms are in place so that you can learn and not keep repeating the wrong thing, I think it's fine. So that capability doesn't exist in existing controllers. So today's controllers are actually vulnerable to that also, because the human designed algorithm or policy does the wrong thing all the time. And it has no capability to do something else. Yeah, sure.
Thank you. More questions?
Hi, I want to ask if there is any simulation data of how much such a smart memory controller could improve the performance of a particular workload. Like if you had some sort of oracle, what will be best for the memory controller to do or something like that?
A machine learning based memory controller, for example. Is that what you're thinking, or a near data processing memory controller? Because all of those could be called smart at some.
Okay, like a machine learning.
Okay.
Enabled memory
Sure.
controller, but if something like that doesn't exist, is there some sort of simulation of how much performance could be gained?
Yeah, certainly. I mean, I didn't want to go into this, but I have a lot of backup slides. Let me give you some data, but take this with a grain of salt because we cannot test all workloads, right? So we did this work in 2006 to 8 timeframe, and we essentially designed a machine learning based memory controller using reinforcement learning principles, because essentially for the reasons that we discussed, and there are benefits to it. This is a paper, and you need to, of course, design the system nicely. But you basically get, I think the 70% over here is the optimistic controller, meaning Oracle. And we get about 20%, 19% of that 70%, which is much better than today's controllers. And I think this is not showing all of the benefits you can potentially get with such a controller. It's just quantifying to a number, but the robustness of this controller is actually much better than many human design policies. Human design controllers go into some situations like your colleague mentioned earlier. They're not smart, but they make the wrong decision and they cannot get out of that. Whereas with reinforcement learning, you can actually get out of this local minima as well as local maxima to try to go to a global optimum. Yeah. So the paper quantifies some of that. Yeah, this one is a paper. And we have some work on more recently on storage controllers. You see even higher benefits in those because the workloads are a lot more data intensive than what we examined, let's say, 15 years ago. Sure.
Thank you very much. More questions? I have one maybe very naive question.
Sure.
In the beginning of your talk, you were talking about genome analysis, and you were talking about the design solution, which includes intelligent algorithms, intelligent architectures, intelligent devices. And I just wonder if it could be extendable to other applications like, I don't know, the star analysis in astronomy
Mhm.
or some other? Is it we can take it and apply to other domain, or there are still some room to set up?
You mean, for example, the FPGA setup that I showed you earlier? Yeah, certainly, I think. I mean, we did it for genomics because we had a lot of experience with it and climate modeling, but certainly if an expert in astronomy developing algorithms can use that sort of system today, even today, to actually accelerate the application greatly. And I'll mention this hopefully if we have time, but we've also been looking at time series analysis, which is used in astronomy, of course, not the entire thing, but time series analysis is another very data intensive workload where you do streaming analytics on data that's flowing. And that's, we showed that you can actually greatly accelerate that with near data processing designs, similar to what we have mentioned for genomics.
Thank you very much.
Sure, you're welcome.
Regarding this RowHammer, does this happen no matter how frequent the accesses are, or do they have to be like at one application happen in a very short period? And
Oops, sorry.
and
This is wrong.
so then does this actually happen in a real workload as well? Or is it
Yeah. These are excellent questions. I'd recommend you to take a look at our RowHammer papers because they answer all of these questions. Well, maybe not the last one easily, at least today. But first of all, yes, it does depend on the frequency of accesses. You should do that before the cells get refreshed, because refresh fixes the problem, right? If you can put in enough activates before the cells get refreshed to induce a bit flip, then it's fine. But we analyze in our more recent papers, like how much does waiting between accesses affect things? And it actually makes it worse a little bit because it leads to some interesting charge buildup effects in the DRAM. So I refer you to some of the papers. That 20-minute talk that I mentioned, it covers all of those works that go into more detail. Does it happen in real applications? So that's a good question. That's so anecdotally, based on our interactions with industry, there are some applications, very, very rare, that exercise this sort of bit flip. It's very difficult to find. But there are some applications that can do it. Today, it may actually be even worse because the RowHammer threshold gets reducing, and some, let's say, benign applications may be opening and closing rows at the rates that may induce bit flips. I think that's where we're headed, basically. If technology scaling goes this way, if you don't have, at least at the raw device level, take out all the solutions that we employ. At the raw device level, if you expose this vulnerability to an application, the application may actually induce bit flips, even with benign access patterns. I don't think we're fully there yet, but we will get there. But hopefully solutions will be in place so that that doesn't happen. But of course, now you think about the solutions. If the solutions have overhead and they kick in for benign applications, now you get performance overhead on benign applications. Right? So you turn the robustness problem into a performance problem, which is probably better. That's why having lower cost solutions is going to be more important.
So my question is about next-gen genetic sequencing, and is the reasons behind pushing this technology to the edge. Because as far as I know, the now existing machines are doing a whole processing of the genomic sequence in about 20 to 30 minutes, and which is relatively short amount of time. And except the flow cost efficiency, what are the other reasons behind pushing this technology to the edge?
Pushing the sequencing device technology to do it faster. I think certainly cost is one reason. The second reason is it's not just about time. Time may be okay. I think 20, 30 minutes can be actually life critical. You may not want to even spend 1 minute. I think it's the first answer is very general in my opinion. Why do you push any technology to the edge? Because it enables new applications. But there's also another reason, which is the accuracy, because the existing systems are good at time, but the accuracy is not necessarily good. They have a true trade-off. Existing devices have a trade-off between accuracy and the read length. So some devices are very good at producing very short reads very accurately, but that makes a computational problem later bigger, because now you need to map really short sequences that they
produced to a larger sequence so that you can really understand what's going on in the larger genome. But some machines have longer reads. They generate longer sequences when they sequence the genome, but they're not very accurate. Like there's 15% error rate, 10 to 15% error rate, and that makes the computational problem also worse, because now you need to be able to map where these sequences are coming from, subsequences are coming from, in the presence of these errors that the machine introduces. I think even if those didn't exist, I think we still need faster devices so that we can enable new applications that we may not foresee at this time.
Thank you very much. More questions? Okay, if no questions, we can.
Okay, great. Cool. Well, how much time do we have left?
We have 11.
Okay. Okay. Okay, let's continue. It's good that people are asking questions. I mean, RowHammer always attracts questions, and I recommend people to take a look at other talks. Okay, so I'm going to give you some examples of processing in memory. And if you're interested, this is a paper that covers at least the current state of the art and also historical perspective. And you can take a look at it. So I'm going to follow some of these over here. But I think my main message is we need to think differently from the past approaches to make them work, let's say. So we need to think a lot about the adoption issues, in my opinion, to make this work. But if you look at the processing in memory literature, the terminology is also not fully, there's no consensus, let's say. I'm going to divide the terminology into two simple terms, and I think it's going to be easy. And I think all processing in memory systems can be classified into these two, but they're very fundamentally different, in my opinion. One is processing near memory. Let me start with that one. Today, memory is here, processor is here, right? And near memory means basically get the processor closer and closer, 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 closer. And at some point, it's inside the DRAM chip or in a monolithic 3D stack. Like it could be multiple processors and accelerators. Basically, you get the processor or accelerator is very similar to what we do today. You get it closer. There's still some decoupling between processor and memory in the fundamental sense. So you still move some data, but the data movement costs reduce greatly. So 3D stacking is a good example of this, or putting the processor accelerator inside the DRAM chip is a good example of this. This is near, basically, near memory processing. I think using memory is fundamentally different. Essentially, you don't think of a processor in the conventional sense, but you think of memory, you start with memory, and you realize that this memory is not just memory. It can also do computation because of the operational principles of the cell as well as the surrounding circuitry around it. And I believe all memories have this capability. And now this enables you to think, oh, this device that I designed as memory can also do computation. How can I exploit that? And how can I design devices that can do both data storage and computation at the same time? Basically, this is really using the operational principles of a memory device to also do computation without adding what looks like logic to us today. And I think this is fundamentally different because near memory is shorter term. Existing algorithms, you push them near memory and they will run, hopefully. So programming is easier, let's say. Whereas using memory, you cannot just push an existing algorithm to run an analog, based on analog operational principles inside DRAM, for example, because it just doesn't work. It's not designed that way. There's no processor there in the conventional sense. So I'm going to start with the first one. I think it's more longer term, but I think it's really more, let's say, radical in the sense that it really doesn't move the data as much as near memory may do. But in the end, I think we probably need to look at both. Okay, and the paper covers some of these. So basically, processing using memory takes advantage of the operational principles of memory to do usually bulk data movement and computation in memory. You can, for example, exploit internal connectivity in the memory device to move data or initialize data, or you can exploit analog computation capability. I'm going to give you some examples from DRAM, which is the main memory technology that we use today. And okay, let's start with simple. We don't even talk about computation. Let's talk about data copy and initialization. This is actually an operation that you do in many workloads today. And this Google paper that I mentioned earlier showed that 5% of their entire data center cycles on all of their data center workloads
is spent on these two function calls, memmove and memcopy. It's actually fascinating that only two function calls lead to 5% of the execution time, because they do a lot of data movement basically. And there are many reasons for it. You can see there are many applications which we cover in some of our papers. But the way we do data copy and initialization today is you bring the data into the processor, copy it to some other place, and then write the data back. Basically, you're exercising the data movement bottleneck all over the system. If it's a 4 kilobyte copy, usually a page copy or 8 kilobyte copy, you're moving 4 kilobytes plus 4 kilobytes data around, let's say. You would think that's not bad, but if you think about initializing a 1 terabyte database, it takes a lot of time actually today, a lot of energy also. So in memory, doing this processing using memory says that, well, why don't you use the internal capabilities of the memory device to actually do this like this and not bother anything else in the system? That's the idea. And this is low latency because we're going to use the internal connectivity and not move the data over huge interconnects and the cache hierarchy. Low bandwidth utilization because you're not going to exercise the data bus over here, and no cache pollution and no unwanted data movement, basically, hopefully. That's the idea. And this is the cost of a 4 kilobyte page copy today. It's about 1,000 nanoseconds, 3.6 microjoules. And what I'm going to describe will reduce it significantly, basically, to 90 nanoseconds and 0.04 microjoules. And you can optimize this more. And the idea at the core level is very simple. If you look at the DRAM subarray that I showed you in the context of RowHammer earlier, these are rows. And each row consists of, let's say, 4 kilobytes of DRAM cells. And you want to copy one row to another row. You basically first activate the source row, which brings the data into the row buffer, which is essentially the sense amplifiers. They amplify the data significantly. Now you capture the data of this row. The next step is to activate the destination row, which deactivates the source row and connects the sense amplifiers, which had captured row A's data to row B, such that the data that was captured here moves to row B. So basically, by doing two consecutive activates, we're exploiting the chart sharing principles that exist already in DRAM that make it work. And you can do it like this. So two consecutive activates, negligible hardware cost, very fast. And how fast it is, basically, what I showed you earlier. It improves the latency of a 4 kilobyte page copy by more than 10x, and the memory energy of a page copy by 74x. Now, this is, of course, if your data is nicely put into the subarray, right? Source data and destination data are in the same subarray. They may be in different banks, and existing DRAM chips have capability of actually moving data between different banks. We don't exercise it today, but you can actually slightly modify things to enable that. And they could be in different subarrays in the same bank. You could also make that to work. So basically, these numbers are reduced based on our recent works and some other people's recent works also. I'm not going to talk about them, but you can do this. You can have the support inside the DRAM chip with very slight modifications because most of the circuitry already exists, that internal connectivity. You can increase the internal connectivity even more to make it better. So that's the idea. That's the idea of row clone. The interesting thing is when we actually wrote this paper, we did all of the things in simulation. And some later works showed that you could actually do this in real DRAM chips, meaning DRAM chip is not designed for it, but by violating the timing parameters in a DRAM chip, you could mimic the operation of consecutive activates, and you could get very robust operation actually, even though the DRAM chip is not designed to do this. So that's the nice part. And we actually repeated those experiments and showed that in this paper that you can do this, and we released this as open source. Basically, we have an FPGA prototype that changes the timing parameters in the memory controller to mimic this row clone operation, and also some other operations that I'm going to talk about, even though the existing DRAM chip is not designed for this purpose. So that's the interesting part. So this is a proof of concept that shows that the behavior is real and you can exploit it. Now imagine what you can do if you actually slightly change the mindset so that you modify the DRAM chip so that it can actually do this sort of operations reliably. Okay, so I'm not going to talk about the copying. So initialization is a special case of copy, actually. Initialization is even easier to support, but you can take a look at some lectures. I think the mindset is really, we're designing a lot of accelerators, and we're very good at designing all of these compute-centric accelerators. Why not think about some accelerators on the memory side also that can exploit the properties of memory? So similarly, we can support in DRAM and or not and majority functions. I'm going to show you an example of this at low cost using analog computation capability of DRAM. activating multiple rows essentially performs computation. And in our prototype, we can actually show that in some DRAM chips, even though existing DRAM chips cannot do this. What I'm going to show you, triple row activation. Some DRAM chips are able to do it by violating the timing parameters so that you can get it to do a triple row activation. And we see and not or functions as I will discuss in a little bit. I think emerging memory technologies enable even more opportunities. There are a lot of works that are going on in this field that I'm not going to talk about, but they actually are capable of what I just described, but they also can do more because you don't need to move the data as much because they're non-volatile. Reads are not destructive in these technologies. So I think the data movement can be minimized even more with these technologies. But also there are works that show that you can do matrix vector multiplication using Kirchhoff's laws, for example, that are quite interesting, but essentially it's the same principle. Those works are crossing using memory examples. You have this memory array that's designed as a crossbar, and you can exploit the analog operational principles of that memory array to do matrix vector multiplication. Let me talk about DRAM. And again, this is, imagine 3 rows, A, B, C. I'm showing 1 cell in each row, but each row can be 8 kilobytes, for example, and you may have thousands of these subarrays. So you can do this in a DRAM chip across 8 million bits at a time, as DRAM chips grow even more. The idea is to do triple row activation. You have 3 rows. If you concurrently activate these 3 rows in a perfect circuit, ideal circuit, you will get a bitwise majority function. Why? Because if at least 2 of these cells are charged, they would dominate the charge sharing. As a result, you would get the charge state at the end. If at least 2 of these cells are discharged, you would get the discharge state at the end, at the bit line over here. So basically, this is a majority, bitwise majority function. It's a great function. You could try to translate your algorithms to bitwise majority, and you're doing bitwise majority across 8 million bits in the system, in a single DRAM. So this is nice. Of course, you can do Boolean transformations, and if C is set to 1, you get the OR of A and B. If C is set to 0, you get the AND of A and B. Basically, now you can now have bitwise AND and bitwise OR in DRAM. So this is nice, but it's not logically complete. For logical completeness, we did not. And not already exists actually. This is the whenever you sense a cell, this is the value of the cell, and this is the complement of it. It exists on the other side of the sense amplifier. You just need to connect it somewhere and have the capability of reading it and probably supplying it to the same subarray. And we actually provide that support also. That requires even more modification, of course. But again, we're not adding logic to do and or not. This already exists in the charge sharing principles that make the circuit work as a memory. Essentially, the good thing is you can now imagine algorithms, any algorithm actually, you can map it to the substrate. It may require a little bit more thinking based on the algorithm you have. And I'm actually going to show you something that makes it a little bit easier because now you have a functionally complete substrate. It may require also some communication with the processor, but you can do a lot of operations this way. And again, as I said, some DRAM chips, while violating the timing parameters between 3 activations, you can get the DRAM chip to mimic the 3 activations. And in some DRAM chips, we were able to replicate the AND and or functionality, majority functionality, basically. Okay, so some algorithms are actually very amenable to this because they already do bulk bitwise operations. So algorithms that like this are algorithms that do bulk bitwise operations. And for example, databases use bitmap indices that are huge indices that can do bulk bitwise operations, web search engines, and you can see basically. When we first came up with the idea, we ported this in a simulator, and we showed that on database queries, you can get significant performance improvements. These are real latency improvements simulated end to end. And you can find more information about the paper in more detail. And there are more works that I'm not going to talk about. I'm going to talk about this one that generalized it a little bit. This was published last year. And the idea is, if you actually have a user, user wants arbitrary operations, right? They don't want to be maybe limited to AND or not. They may want a convolution, for example, and they specify with AND or not logic, and we convert it to an efficient majority, not logic. And these are using electronic design automation tools. Some of them were developed actually at EPFL at Nani's group over here. So we use some of those to optimize this logic. And then we convert it to a microprogram that can execute this operation. You can think of this as a convolution. And that microprogram gets stored in the memory controller. And the user inserts an instruction. And that instruction essentially triggers that microprogram. that essentially performs the operation in the memory controller. So this simplifies the process for the user. There's a lot of operations that we show can be supported this way, but any operation can be supported this way. Of course, there are system level issues that we will hopefully talk about, maybe not, but that need to be solved, and the paper covers that. Now, if you actually have this sort of thing, now you can actually support complex operations, not just and or not, but you can build convolutions, you can build multiplication clearly, you can build divisions, and we analyze all of those operations. And you can see that the performance improvements and energy improvements are significant compared to CPU and GPU, existing CPUs and GPUs. And I think there's a lot more potential going forward in this work to improve the efficiency and performance. Like supporting complicated operations usually is not easy because we start with the basic and or not, or majority and not. There's room for optimization basically. Okay, and that's the work. Similarly, you can actually employ physical unclonable functions. This again, based on the characteristics of memory, there's a trade-off. As you reduce the latency of the memory, some cells become unreliable, and some cells form a signature of the device. And this is a physical unclonable function. You can now identify the device if you know which cells are behaving this way. Some cells randomly fail, meaning if you reduce the latency, some cells start randomly failing. So if you identify which cells randomly fail, this is a true random number generator for you inside DRAM. So by exploiting the latency reliability trade-off in DRAM, you can build puffs and true random number generators. You can build better true random number generators. This is quadruple row activation that leads to a better true random number generator, it turns out. And you can build an end-to-end system support to enable these true random number generators. So you can build a security substrate on the memory, just exploiting the operational principles of memory as well. So there's more we can talk about, but I think we don't have a lot of time. Let me jump into the processing near memory side, which, as I said, is more shorter term and easier to do. As a result, all of the prototypes for processing in memory today are processing near memory. As far as I know, processing using memory requires some more work, even though existing DRAM chips are capable of it. I'm going to talk about some applications and how they would benefit from acceleration on the near memory side. I'm going to start with graph processing because it's an application that doesn't scale very well. You could add a lot of computation capability, but you're bottlenecked by memory. You can see this number over here. You quadruple the number of cores, you get only 30% performance improvement. It's very similar to the AMD's cache that I talked about earlier. Right? So the reason is you have frequent random memory access, frequent enough. Not everything is random, but frequent enough random memory access, but little amount of computation. So we're going to take advantage of 3D stacking that looks like this, logic layer underneath memory layers. And this logic layer, you can build processors that can have low latency, high bandwidth connectivity. And I think Subhashish will probably talk about better 3D stacking approaches that are monolithic, which I think will make this even better. But we're inspired by the 3D stack memory technologies, and we're going to add compute units in the 3D logic layer. And these compute units are going to ship functions to each other that operate on data. So they're going to be programmed based on remote function calls, remote procedure calls, very much similar to distributed systems programming today. So we have in-order cores. On top of the in-order cores, you have some memory associated with them. And you don't move the data between the cores, you move the functions. So if one function wants to update some node, it sends a message to the node that hosts the data that is need to be updated along with the temporary value, and you update that data in place as opposed to moving it all around. And that's the idea. And if you want to scale up the system, you basically add cubes, but of course there are communications that are off chip across the cube. So you need to be careful about how you map your graph. So that's the idea. It's a whole system level paper, so I'm not going to talk about the details of it. We cover a lot of the aspects of the system. But in the end, if you design it nicely, you get significant performance improvements. And this is essentially what Tesseract looks like. Tesseract is a three-dimensional hypercube, but it doesn't look like existing systems which have the processor memory dichotomy. It has these 3D stacked memory plus logic chips that are interconnected with each other, and they get exposed to very high levels of memory bandwidth, as you can see at the time. Today, actually, this number is much larger, let's say. And the performance improvement end-to-end across 5 different graph processing algorithms is more than 13x. And this is old. We did this work around 2013. It was published in 2015. Later works improved on what we did. And I think they input a lot of system level aspects, data mapping, graph partitioning, interrupt handling, etc. And they showed that you can actually get 2 orders of magnitude performance improvement right now We showed like 8x energy reduction, and later works actually improved that almost close to 2 orders of magnitude also. This shows that if you can actually design a system near memory and somewhat specialize it for graph processing. We didn't go all the way to specialize it. It's not, these are really still in order cores that are executing graph processing. And there's a reason why they're in order, because we cannot afford complicated cores and they don't make sense in the logic layer of memory for technology reasons and terminal reasons, as well as application reasons, because you don't get a lot of benefit. If you specialize the cores, you would get even more benefit. And that's the paper that introduced it. Now, let me take a little bit more time to talk about some more applications, and then we're going to conclude. Is that okay? Or?
Yeah, feel free to have fun.
Okay, sounds good. And if you want to stop me, feel free to ask questions. That's a good way of stopping the high bandwidth communication. Okay, so I'm going to mention this work that I mentioned that we did with Google, just to give you an example of. So this work, some of these works change the entire system, right? For example, in this Tesseract system, we assume we have all the freedom to change the application, change it to a completely different programming model, get rid of the virtual memory in the system, get rid of cache coherence. So it's nice, of course, but real world, maybe you don't want to get rid of everything at the same time. And that's what we wanted to understand over here. And we examined these 4 applications with Google. And I already showed you this data point. Most of these applications actually spend a lot of energy on data movement and also performance. And we identify some functions. It turns out there are some very simple functions that are actually very intensive in data movement. And if you actually offload them to near memory engine, you can get a lot of benefits. Maybe not 13x or 100x, it's going to be 2.3x or so, but still a good start because you're not changing a lot in the system. We look at PIM cores and PIM accelerators, and that's basically the major result. You identify some simple functions to offload as opposed to redesigning the entire application to fit a system like what I described earlier. Let me give you some examples. In machine learning inference, for example, mobile inference, we found out that more than 50% of the inference energy is spent on data movement, and 2 functions are responsible for half of that data movement. And these functions are really easy to implement: packing, unpacking, and quantization. Very data intensive and not compute intensive applications. And you can see more of these applications and more of these functions inside this paper. Compression and decompression are other examples, for example, and motion estimation and video is another example. So I can give you more examples, but we don't have a whole lot of time. So GPUs can benefit from this also. You can offload some simple memory-intensive GPU tasks to simple GPUs in the logic layer. You can do it transparently, but you can offload linked data structure computation, which is very latency bottlenecked to simple accelerators in near memory, but we don't have time. Now, this is the climate modeling that I mentioned earlier. Okay. Yeah, this is the time series analysis that I mentioned based on your question earlier. So there are a lot of example applications, and I think these are fascinating because these are examples of algorithm architecture co-designs. And some of them actually propose other things like if you're operating on sets, you can actually make it a general programming model as well, more set-centric programming model, and a lot of graph algorithms with that set-centric model, which is quite interesting. If you're interested in that, we have works in that direction also, and database systems are other examples. Maybe I'll mention neural networks a little bit. We've done the study with Google also to understand their edge devices and how they're bottlenecked. But basically, we analyzed a bunch of the proprietary Google edge models, and we found out that you have monolithic tensor processing unit accelerators that are very highly provisioned for on-chip scratchpad memory as well as computation units. But this monolithic accelerator doesn't handle all of these machine learning layers really well. As a result, we decouple the accelerators, have 3 accelerators in this particular case. One of them is compute-centric, 2 of them are data-centric, near memory. And based on the characteristics of the layer, we execute the different layers on different accelerators. And that's the idea over here. I'm going through this relatively quickly, but that's the key idea in the end. And this stems from the fact that different layers have very different characteristics. So you can, for example, this is classifying different neural networks based on their parameter footprint as well as arithmetic intensity, right? And you can see that it's all over the place. There's a huge variation. Also, within a layer, there's a huge variation also. For example, in flop per byte, you get 248x variation across the execution. So it makes sense to have not a monolithic accelerator, but different accelerators that are customized for different families of these layers.
and have a runtime system that classifies these layers so that they're executed in the best accelerator, and two of which are data centric. I'm not going to go over that right now, but these are also have their data flows customized so that you can minimize the data movement. And overall, the interesting thing here is if you actually design an accelerator that looks like this, heterogeneous, it's faster than the monolithic accelerator. It's more energy efficient, about 3x in both cases. It's also more area efficient. So overall real estate you spend is smaller than what is spent in HTPU today, because this is provisioned very high. But it suffers from what I showed you earlier. It's processor-centric. The system has a lot of computation, a lot of memory, but most of the time it's not using it because it's processor-centric basically. So you can actually get rid of the inefficiency in the hardware real estate as well by designing multiple accelerators overall. So having 3 accelerators is cheaper in terms of area compared to having a one monolithic accelerator that's designed today. Okay, and that's the paper that summarizes it. Okay, I already discussed this. But basically, we need to revisit the entire stack to do all of this. I think one important issue is how do we enable adoption? So I think I will conclude with this one. So there are many, many barriers to adoption clearly on a new technology, and that's always true. Here, it's not just the technology, it's also the affects everything in the stack, right? And these are 5 major things, clearly, and most of them are about software and systems. How do we design software and systems to enable this? And programming interfaces, system and security support to enable this, runtime and compilation systems, and infrastructures to truly assess the benefits and feasibility of these mechanisms. I think this is really important to develop to enable a paradigm shift like this. But maybe the most difficult thing is the mindset, because as I said, the processor-centric mindset is ingrained in everything we do, even though we don't recognize it initially. Like today, data mapping, that's a simple one, is optimized for the processor, right? Because processor is where the data is processed. That's the only place data is processed. You basically spread your data all over memory channels. This is terrible for processing in memory. Processing in memory requires your data to be localized inside one memory chip because that's where the data gets processed. So that mindset has to be, let's say, thrown out. And you need to really start with a different mindset to enable the data-centric paradigm. And I mean, you can see this in, so for example, when you write papers or give talks, people say, oh, but data mapping doesn't work that way. Yes, it doesn't work that way because this is a different way of doing things. So I could say this for many, many different way of doing things today. Okay. Okay, I'm not going to talk about the adoption issues, but clearly the reason we're looking at a lot of these key applications is an adoption issue, right? Well, how do these applications benefit? Okay, I think we're out of time. Maybe I can give you some examples in the real world and then we'll conclude. So the good thing is if I was giving this talk, let's say 3 years before, or even maybe 2 years before, okay, I wouldn't have these real examples. And I was giving this talk and I didn't have these real examples. Now I have these real examples that I showed you. Let me cover them very quickly. So this is the UpMem company. They're in Grenoble and we actually work with them. They have these real DRAM chips and they have processors inside the DRAM chips. If you're interested, we have papers on it. You can take a look at them. But basically, this is near memory computing. Each DRAM bank is equipped with a simple multi-threaded processor that looks like this. It's not as simple as processors in the 1990s, of course, but okay. But basically, we released benchmarks for this and you can find them online. And some of them do really well, even though the computation capability inside these processors is not very good. They don't even have a multiplication operation. But some workloads benefit a lot, even though there's no multiplication operation here. Because they're so data intensive that you don't need that multiplication operation to be natively supported. I'm not saying this is the best thing to do, of course. I think over time, people will add operations to these processors inside DRAM. Okay, that's one example. I'm going to skip this one. We do a lot of work on identifying which functions should be offloaded. If you're interested, you can find this. But I'm going to give you a couple of quick examples of Samsung introduced their DRAM chip that can do some machine learning acceleration. They have some papers. You can take a look at them. This is the ISSCC paper that looks at it. But the good thing is it's a real prototype that can do, that's essentially specialized for multiply and accumulates. They also have DRAM modules that can do recommendation acceleration together with Facebook, I believe. They have also papers. SK Hynix more recently this year introduced their accelerated memory that actually adds even more modifications to DRAM, which is interesting in GDDR6. And Alibaba has their prototypes also. So people are actually experimenting with these prototypes. We will see how successful they will be.
So adoption is still an issue, even though these big companies are pushing. But the good thing is there are people who are really pushing it right now because they're feeling the, let's say, heat from the technology as well as the applications. They need to do something different. Okay, and the future may be even better. Okay, I think I'm done. I'll share these slides, and clearly we don't have time for other parts. Maybe this is how I'll conclude. So basically, I think we need to do, I changed this recently to we have to design systems to be truly balanced, high performance, and energy efficient. That will lead us to intelligent systems. And I think that requires being data-centric, data-driven, and data-aware. And hopefully I've given you some examples of how this can lead to orders of magnitude improvements, maybe enable new applications and computing platforms, and who knows, maybe enable a better understanding of nature in the end. Because we're really going against our principles when we design processor-centric systems, which is the balanced design principle. But we were probably also not doing a great job imitating the nature if nature actually does some things in a more balanced way. But we need to do more research. Maybe some of you will do that research. I'll stop here because we're already over time.
We have room for one question, one out of one, but if you have a question, please. Okay. So.
So when we're talking about some of the operations, all this stuff, the hand, the boards, etc., you mentioned it could also be extended to method matrix multiplication. Do you have any figures on that? That seems like, inference pretty useful.
Yeah. So we don't have, it's not our figures, but other papers have figures. So they do it in crossbar based resistive memories, for example, and they show huge improvements. Now, you could argue how much of it is realistic. A lot of these are simulation based. There are some prototype chips that are also being designed in conference like ISSCC, for example. I'd refer you to those papers, but we did not do that research ourselves. But the figures look quite good. Of course, there are challenges with these technologies. Right? There are a lot of reliability challenges to make this matrix multiplication work. If you want to scale the size of the array, reliability becomes an even bigger issue. And the conversion overheads, which are sometimes not taken into account in some of those works, may reduce the benefits. But no, it's basically it's Kirchhoff's laws. So you could build Kirchhoff's complement on top of this if you want. But yeah, but when I said conversion overheads, it's not the software format conversion. It's the analog to digital conversion overheads, because you have this analog portion of the array, and then at some point you need to sense it. So if you make the array too big, your reliability issues make the sensing circuitry more complicated as well. But I think it's a good direction that people are exploring, and the numbers look quite good, but it all depends on your comparison points also. So we have some work on real systems, but not on that sort of system. So in the, we actually took this tough task. So this UpMem system, for example, it doesn't even have multiplication, right? And we wanted to understand its benefit on sparse matrix vector multiplication. And even in the system that doesn't have any multiplication support near data, you can get some benefits. It's not as much as you would like. So without multiplication support, how do you do multiplication, matrix vector multiplication, right? But even in that system, because data movement overhead is so large that you can get some benefits. This was published in Sigmetrics this year. And we have some upcoming work that propose better multiplication mechanisms to take advantage of it. Well, some multiplication mechanisms that are low cost. But it's not going to be as efficient as those analog emerging memory-based matrix vector multiplication, of course.
Thank you, Onur. Thank you. And try now a small break and then continue in 10 minutes. So, thank you very much.
Thank you.